Today we are going to continue with what we had done in the last class, that we are going to continue with the kinetic theory of gases. Probably we will be doing this for a few more classes, but what we had done in the last class was we had tried to derive a pressure expression for pressure in terms of the conditions where we had taken that the molecules were colliding with a particular surface of the container. We had the total volume of the container V, and the total number of molecules which were colliding on the surface and at a given time was found out, and from that we got an expression for pressure. Now, what we are going to look, if you remember, the expression for pressure was given something like this in the last class, where this was the volume of the total container, this was the pressure of the gas which was generated when the molecules or particles of the gas were striking the wall of area A within the distance of the distance was taken to be Vx into delta t. Within this, this was considered to be the length of within which all of the particles which were striking on the surface of the wall area A were found out, and from this amount of whatever the rate of momentum which was transferred divided by the total area of the container on the wall was found out, and from that expression, because force by area is the pressure, and the force was found out from the rate of change of momentum. The rate of change of momentum, total rate of change of momentum was found out, considering a number of total number of collisions which were occurring, that into the change in momentum for one collision. Okay. From this expression, what we had got the velocity which what we had taken as the velocity of the particles that were moving in the x direction. And why we are taking, and why, what velocity, what is the term which we are going to call this? We are going to call this as the root mean square velocity. The particles which we contain in the unit volume or the total volume of a gas is equally probable to be colliding in all the three surfaces. That means they are moving in x, y and z direction with equal probability. So, if we look into that, we again visit what we were taking in the previous class. We had a unit volume, total volume of this container which was cubic, was taken to be V, with each of the length of the volume being L. So, the velocity of the gas molecules was represented as its velocity is a vector. So, the x, y, z components of the velocity exist. So, we have to not only take consideration about the magnitude, but we also need to take account of the direction, because vector means we will have the x the magnitude as well as the direction associated with the vector velocity component. But more often we will be more interested in the magnitude of the velocity vector instead of the direction. The magnitude of this velocity vector is a scalar term which we call as the speed. So, velocity is a vector term which has magnitude and direction associated with it. We are looking into the velocities of the molecules which are moving in a system or of a volume or of a cube of side length L, total volume be equal to L cube equal to V. So, all the molecules contained in this, we are talking about them exerting pressure on the wall through collision, and we are looking in the vector velocity space where the velocity of the molecules or the particles are resolved into x and y and z direction. We were interpreting the entire derivation only considering that the particles were moving in one particular direction, that is x direction, parallel to the x direction and hitting the surface which was on the right hand side. So, now if we are looking into the speed, what we are looking into? We are looking into the speed of the molecules. What we write here this as the speed can be calculated. Speed, we are talking about only the magnitude part of the vector velocity vector. The speed can be calculated from the Pythagoras theorem. Using the Pythagoras theorem, you can find out what the speed will be, because you have the x, y and z component of speed velocity. Only considering the magnitude of it, we can calculate using the Pythagoras theorem the velocity being the under root of the velocity component in the x, square of the velocity in the x component, plus the square of the velocity in the y component, plus the square of the velocity in the of the z component. So, the c which we are looking into, which we are calling as speed, is also known as the root mean square velocity or root mean square speed. So, what is actually happening? What is actually happening? What we are seeing, the velocity component which we are looking into, we are looking into this component of the velocity. It is the particles are moving, hitting, striking the wall, and this is the wall with the area A, and there it is reverted back or moving back in the opposite direction. What we are looking into? We are looking, that means what is possible, that the number of particles which are striking the wall having a velocity plus v there's likely that the same number of molecules will be there with the velocity minus Vx. So, you need to realize this before we go into what is the root mean square velocity. We are going to be interpreting the pressure and the kinetic energy of the molecules based on certain assumptions, like what we have done in the previous class, that the molecules which are striking are undergoing a perfect collision or a elastic collision, where the total kinetic energy of the molecules is conserved. Okay? What do you mean by that? If you look into a picture of what usually happens when you have an elastic collision or a perfect collision, what you have is you have a particle which is moving with a certain set of velocity. It strikes another particle which is in the same volume element, and after striking, this molecule will be moving with another velocity, maybe the same velocity or different velocity, moving in the same direction. So, the total kinetic energy and in an elastic collision, the total kinetic energy and the momentum of the particle remains the same. But when we have an inelastic collision, then we do not have conservation of total kinetic energy, but there is a conservation of momentum. Suppose you have an explosion, and in an explosion, then the number of particles moving away from as splinters, this splinters will have the condition where we have the momentum of the particles of each of the particle which is coming out in the explosion will be same, but the total kinetic energy may not be the same. For example, when we look into an inelastic collision, it is colliding and it is reverting back in the same direction. The total kinetic energy is not transferred or is not held constant. When we are talking about a particular molecule, the kinetic energy of after a collision may not be exactly the same, which may not be exactly what it was before. That means we do not have exactly for each particle the conservation of energy is not held, but overall in the set of particles in a volume, the total energy of the kinetic energy of the system is conserved when they undergo a elastic collision. So, this is to be understood very clearly. Now, what we are looking at, we are going to interpret the pressure and the kinetic energy in terms of the colliding particles. So, if we are doing that, let us come to the previous slide where we were talking about it. So, the slide which we had last ended in the last class was where we had given the expression of pressure, where this V was the total volume of the cubicle which we were considering, in which the gas was enclosed. This was the number of moles of the gas, and this was the molar mass of the gas which we had used. If you remember the expression that what we derived in the last class, this was the last expression we had stopped in our lecture. What is this? This is the velocity which we are writing as Vx. This is the x component of the velocity, the resultant velocity which is along the parallel to the x axis. So, now what we are saying, since the molecules are in complete random motion, there is no preferred direction that the molecules will go in x or in y. The molecules will have a tendency to have either going in the x direction or in the z direction or in the y direction. They have equal chance. There is no preferred any set of direction. They have equal chance of a particle moving with a velocity x along the x axis. The same is a particle moving with the velocity y in the y direction and the velocity z along the z direction. That means the probability of having any of these velocities by a particle should be equal. They are equally probable to have either this or this or this. So, to find out what will be the velocity what we can take, that means the velocity which we can have is either 3 times this or 3 times x or 3 times y. So, if we want to find out what is the velocity in the x direction, what we can say, this is what we call as the standard absolute velocity or the root mean square velocity, which should be equal to 1 by 3 of the root mean square velocity. So, the velocity component along the x component will be nothing but the root mean square velocity divided by 3, because they are all equally probable. So, if I have that, then I substitute that in the expression I have for this, for the Vx component. Vx is what? We can write the velocity square, this is the RMS velocity or the root mean square velocity divided by 3. So, this comes from this expression where all of the velocities are equally probable. So, the root mean square velocity will be either the 3 times of any velocity in any one set of direction. So, the velocity at one set of direction will be given by nothing but by the root mean square velocity by 3. So, here we are going to substitute this into this expression. What we get is going to be something like this, right? Have a look at this. What we are substituting? We are substituting n equal to number of mass of the molecule divided by the molar mass, or it can be represented by the total number of molecules divided by the Avogadro number. So, if I represent that by the total number by the n by the total number of molecules divided by the Avogadro number, substitute in this, what do I get? I get, and the total number of molecules is nothing but the mass of the molecule divided by molar mass into the Avogadro number. So, if I substitute this here, I get the expression. Can you just have a look, do it yourself, and only then you get to write what you are seeing here. So, what you are having here, this is the total number of molecules, this is the mass of the molecules, and this is the total volume, and this is the RMS speed or RMS velocity, which is nothing but the under root of velocity square in all the square of all the 3 components, like we have written here. This is the one which we are looking into. Sorry, these things happen. So this is the velocity we are looking into. The root mean square velocity which we are representing is the under root of the mean velocity, the root mean square. That means you are taking the under root of the mean square of the velocity. This is the mean velocity, you are squaring them up and you are taking the under root, is how you define the root mean square velocity. So, it is the square of the mean velocities along the x axis, y axis and the z axis, and summing up them and taking under root gives you the RMS or C value or the RMS speed. So, if we have come to that, we have now justified why we are having the 1/3 component. So, 1/3 component is now introduced in the pressure. So, if we now represent this, we take the volume to this side, then what you have? We have an expression which is quite similar to the inert gas law, where we have PV equal to nRT, and here we have PV equal to 1/3. This is N is the total number of molecules, this is the mass of the gas, and this is the RMS speed. So, we have derived the expression which in terms of the speed of the molecules, the RMS speed of the molecules, so that we can find out, interpret in terms of the speed of the molecules, in the pressure in terms of the speed of the molecules. So, next we move on to the relationship which we have just now obtained. This can be rewritten, you can manipulate. See what I have done. I have got the same expression as the one which was there previously, m into v, 1/3. It was 1/3. What was it? N m root mean square velocity. This was given to be the pressure. What I have done, I have, and that was divided by V was the expression of pressure which we had. Now what we had taken, now we manipulate, we multiply 2 in the numerator and also multiply 2 in the denominator. If I multiply 2 in the denominator and rearrange the terms, then what I can take? I can take this separate out, okay? This can be separated out and this another portion can be separated out. What we are looking into here is we are trying to relate the macroscopic value of pressure which we are using in the ideal gas laws, or the which is the expression which we use in the gas law equations. So, this is that pressure which we are talking about in the macroscopic term, and what we are trying to relate? We are trying to relate the macroscopic quantity of pressure with terms of the microscopic quantity in terms of the average or the square of the velocities of the molecular velocities of the particle, and the proportion. We have also found out the pressure is proportional to the number of molecules per unit volume. So, what we are seeing, pressure is proportional to the number of particles in the unit volume. We are also seeing that pressure is proportional to the root mean square speed, okay? And this equation also tells us that pressure, as the pressure of the gas can be increased by increasing the number of particles in the volume, in the unit volume. That means, if I increase the number of particles in a unit volume, the pressure should increase. Similarly, it also tells pressure can also be increased by increasing the speed. So, interpretation of pressure from the kinetic molecular theory is what we have just now concluded, is we have derived initially the expression of pressure based on the collision theory, and from that collision of the molecules with the walls of the container. From that, what we have interpreted is the pressure term, and from this pressure term we have seen in the volume total volume V, if the n is the total number of particles, how it is going to be dependent on number concentration of the particles, or the concentration of the particles, number of particles in the unit volume, and how it is also going to be proportional to the number of RMS speed of the particle. So, if you increase the speed, the pressure is going to increase. If you increase the number of molecules, the pressure is going to increase. So, these are going to give rise to this part. Is also, if you are looking into this part, this is going to be something in terms of the kinetic energy. So, we can also the pressure is proportional to the number of particles and to the average translational kinetic energy, because we are taking the movement of the molecules in either x or y or the z direction. So, what we have found out, it is proportional to the translation kinetic energy, it is proportional to the total number of molecules present per unit volume of the container, and it is proportional to the speed. So, the pressure can also be increased by increasing the speed, we can increase it by increasing the number of particles. So, this being what we have derived, now we can go into the expression what we can in terms of the energy. What we have taken? We have taken the pressure we have found out what the pressure is, and from the pressure expression we know that this is the pressure which we have derived from the kinetic model, and if I take V to the other side, I can rewrite as 2 by 3 n into half mc square. This is the root mean square velocity. Similarly, I have another thing which can be obtained, which from the ideal gas law. From ideal gas law, we know this PV equal to nRT. Now, I substitute n with n by number of molecules by the Avogadro number, because n is this is what the number of moles can be represented. So, PV equal to n by the Avogadro number into the R into T, and if we know another relationship which is a Boltzmann constant. According to Boltzmann constant, the gas constant by the Avogadro number is equal to the Boltzmann constant. So, I can rewrite the whole thing in terms of the Boltzmann constant, PV equal to KT, and this K usually we do not say KB, but we say it is KT when we say, but it is actually to represent that it is a Boltzmann constant that I have written the subscript B. So, what we have? We have two expressions of PV. Just have a look. This is what we have just now derived from kinetic model, and this is what we have from the ideal gas law. Now, equate these two. If I equate these two, what do I get? If you equate these two, this is what we have for from PV ideal gas law, and this is what you have for the inert gas from kinetic model. Now, if you can look into this very closely, this C is the root mean square velocity. This is nothing but the root mean square velocity, which is represented in when I say it is in terms of Vx or Vy, Vz. So, this is the root mean square velocity which we have. So, what we have equated? We have equated this to this. What we have gained from this is half mc square equal to 3 by 2 kT. This is something very familiar to what we know about the kinetic energy of a particle. When we talk about the kinetic energy equipartition law, let us go to that and let me show you that. Okay. So, we have this expression. From this expression, what we have, this is half mc square is nothing but the kinetic energy. So, the average kinetic translation kinetic energy can be represented by this. This is the representation of the average kinetic energy, translational kinetic energy, and that is equal to 3/2 kT. So, if I rewrite that, I can rewrite the translation kinetic energy, this equal to nothing but 3/2 kT, and that is kT is what? K is R by the Avogadro number. So, I can rewrite this as the kT as R by the Avogadro number. So, this is what we are going to get. So, what we are having for n number of ideal particles in a cubical container, the total average kinetic translational kinetic energy can be given by the total number of molecules into the total the kinetic energy per unit molecule. So, this is the total kinetic energy which we get for n number of molecules of ideal gas in a cubic container, with the total average kinetic energy being represented by K. So, this is what we get. So, if we talk about in terms of the principles of equipartition of energy, the mean average kinetic energy of every degree of freedom of molecule is represented by half kT. So, depending on what is the degree of freedom, you have degree of freedom into half kT, the mean kinetic energy per molecule. So, if we want to find out the mean kinetic energy per mole, we will write this will be nothing but K is what? R by the Avogadro number. So, if I have, so this is what we have got. So, this is what we are establishing is the I was trying to write down what the Kb was, the K, this is the Kb or the Boltzmann constant. Boltzmann constant is nothing but R by Avogadro number. So, what we have got is what is depending on the degree of freedom, depending on the type of molecules we are dealing, we can find out the mean or the average kinetic energy per degree of freedom of the molecule, which is equal to half. We have to multiply by the total number of molecules, total degrees of freedom which we have, and hence we can get the total kinetic translation kinetic energy. Now, we have obtained these information of pressure and kinetic energy. Now, I would like you to interpret how, if I increase the pressure if the temperature is held constant, if I increase the pressure, what happens with the volume? It is decreasing according to Boyle's law, and if I have this expression represented like this, if this is the initial condition, you have number of molecules, the pressure, temperature, volume is held at constant. Now, if I increase the temperature, if I keep the pressure constant, if pressure is held constant, the total weight on the, suppose it is on the constant, what happens if I increase the temperature? What I have, if I increase the temperature, what happens? The kinetic energy of the molecules will increase. They will be moving around with a much higher speed. So, what will happen? To maintain the pressure constant, what will happen? The gas has to increase in volume or expand. Similarly, if I have the original volume constant and I have the pressure, if I increase the pressure, what will happen? Since the volume is now reduced and the number of particles which are held in that particular is constant, and it is continuously colliding and moving around in the random speed, what will happen with the confinement of the volume? If you are increasing the number of particles or increasing the pressure by, say, temperature is constant, you are putting more weight, the pressure, the volume is reduced, the pressure is increased, and the volume if the volume has to be held constant, what has to occur is increase in temperature, because the number of collisions will be increasing. So, if your number of collisions are increasing, they will give rise to the rise in the temperature. I would like you to do this interpretation of the various laws in terms of the kinetic theory and judge yourself. Okay. So, this is what we are going to be looking into. So, I leave to you to interpret the various gas laws in terms of the ideas or properties which we have just now established in terms of the kinetic energy of the molecule, in terms of the speed of the molecules, in terms of the total number of molecules in a particular volume. Okay? Thank you.